Welcome to ASHRAE's Tech Hour. Today's subject, building decarbonization, electrification, for hydronic systems. Our speaker today is Mick Schwedler, Staff Applications Engineer, Train, La Crosse, Wisconsin. Mr. Schwedler was ASHRAE's president for 2021-22, is an ASHRAE Fellow, and recipient of ASHRAE's Exceptional Service, Distinguished Service, and Standards Achievement Awards. He has served as chair of ASHRAE's Standing Standards Project Committee 90.1, and chair of the Advanced Energy Design Guide Steering Committee. Mr. Schwedler has also served as chair of the USGBC Lead Technical Committee, served on the Lead Steering Committee, and is a past member of several USGBC technical and education groups.
Today we'll be talking about building decarbonization or electrification, and we're going to be talking about hydronic systems. You can see the learning objectives on your screen. I don't read them to you, but we're going to be talking about what is decarbonization, electrification, what can you do about it, and then we're going to spend the majority of our time today discussing the hydronic systems in order for us to electrify the heating in our buildings. What's not on the agenda? We will not be talking about embodied carbon. There are many other folks like Luke Leung, a distinguished lecturer at ASHRAE, who can take care of that for us. And we also won't be talking about financial analysis. However, I will have a single slide near the end about finances. So we're here today to talk about decarbonization or decarbonizing. So let's define that. It's basically reducing or eliminating the carbon emissions. Now, many people use the term electrification as if it's synonymous with decarbonization. I don't. And the reason is because I don't think it really is. Electrification is something where we're using electricity in the building to provide the heat rather than burning fossil fuels. It might decarbonize, and it certainly does reduce the carbon emissions of the building. However, depending on the electric grid to which the building is connected, that will depend on whether or not we reduce the carbon emissions. So let's make sure when we're looking at this that we separate those two if we want to consider all our environmental emissions. So from a standpoint, our building is connected to an electric grid, and the theory is that as that grid becomes lower carbon, for example, by using renewable energy sources that don't emit carbon, we will, when we electrify building heating, also reduce the overall emissions. However, remember that the total difference in emissions reduction is going to be dependent not only on what we do at the building, but also the electric grid that we connect to. The next thing we're going to talk about is refrigerant selection. Now, from a refrigerant selection standpoint, what can happen is refrigerants have a global warming potential. And what's on our slide here is a 500-ton system with different refrigerants. Some of them are in use today, the ones on the left side of each of the charts. And the others are coming into play today as we start to phase down the refrigerants with higher global warming potential. So we can see on the left, we have high pressure equipment like unitary package rooftops. In the middle, medium pressure, those would be for screw chillers and some centrifugal chillers. And then low pressure refrigerants for centrifugal chillers only. And we can see that for the medium and low pressure refrigerants, that they have refrigerants with zero or near zero global warming potential. However, the high pressure equipment does not have zero or near zero GWP refrigerants available today. So we're going to still have environmental emissions and CO2 equivalent emissions. But that assumes that the refrigerant leaks out of the unit. One of the things we can do is follow ASHRAE procedures to make sure the units are tight, that they don't leak, and that we have a plan in place to keep that refrigerant in the units. Then we will have no direct effect on global warming with respect to refrigerants. Our next learning objective, we're going to look at the hydronic systems. And we're going to talk primarily about the hot water temperature and the heat source temperature, because those affect all the equipment that you're going to be using within the buildings to provide heat. We're going to start out with hot fluid providers. How do we make that water hotter? Well, there are two different types of units. First are the air-to-water heat pumps. They take heat from the outdoor air, they send it through a refrigeration cycle, and they reject that heat into the hot water stream of our building. These are air-to-water heat pumps and even water source heat pumps, as we'll see in just a few minutes. The next one is a water-to-water heat pump. This could simply be a chiller, but we're using the water from the condenser in order to provide heat. So it's a heat recovery chiller. It's what's called a chiller heater, which could act either as a chiller to provide cooling as its primary source, or a heater to provide heating as its primary reason. And then a water-to-water heat pump is also an example of this. And we'll look at some equipment. So from an air-to-water heating system, we might have a two-pipe changeover system. On the top here is a packaged air-to-water heat pump. On the bottom is a modular. And we'll talk about some of the advantages of each in a few slides. Another air-to-water heater is what we often think of as a water source heat pump. But most of the time, we're thinking about it operating to satisfy the air temperature in a space, for example, a hotel room. It can be changed, and its usage can be changed, as we'll see, to provide hot fluid. And we'll look at that in a couple of slides. Now, an important aspect to understand about air-to-water heat pumps is that its performance will depend on the outside air or ambient temperature. So when we look at this chart, we will see that the capacity of the unit when we go from 60 degrees outside air to 0 degrees drops by about half. At that same time, the power to produce the heat increases. And what that means is there's a term called the coefficient of performance. And the COP is the useful work we get out, in our case, our heating, divided by the power input, and it's in the same units. So at 60 degrees, we have a COP of 4. That is, we get 4 units of useful heating out for every unit of electricity we put in. But frankly, we don't do much heating when it's 60 degrees out, do we? So how about at 45 degrees? Well, that's a COP of 3. Again, we're not doing a whole lot of heating. I'm in Wisconsin. When we get down to 15 degrees, we're in heating. There, the COP is only 1.5, which means we need to use a lot more power to get the same amount of heat out. And if we get down to 0 degrees Fahrenheit, that is a COP of 1, which is the same as electric resistance heat. So when we're thinking about the building that we're going to heat, we need to know about this performance and determine how we're going to apply that piece of equipment in that local application. Another important aspect is between about 45 and 0 degrees Fahrenheit, you lose about half the capacity. So the owner has to buy double the equipment size, and that's an increased cost. Next, let's talk about re-rating the heat pump. Heat pumps are rated by the ASHRAE rating standard at 47 degrees Fahrenheit. But again, we're not doing much heating there. What if we're someplace like Atlanta, where the temperature is 4 degrees on a design day? Well, we will see that we need to re-rate that piece of equipment. We get lower capacity from that piece of equipment. And in fact, once we get below about 15 degrees Fahrenheit, that equipment can no longer satisfy the full heating load. So we will have to have some additional heat available or even some backup heat. So we need to re-rate the heat pump for the specific application. Now let's look at what happens to both capacity and efficiency for that air-to-water heat pump. We can see that as our heating capacity goes down, as the hot water temperature goes up. So not only do we have to be concerned about the outdoor air temperature, we need to think about what our design hot water temperature should be. If we provide hot water at 95 degrees, we get one capacity. At 135 degrees, we lose about 60% of our capacity and about 32% of our efficiency. Now, I'll share that the hot water temperature is about the only thing that you have that you can make a decision about. All the other impacts are external forces. What's the building load? What's the outside air temperature? So knowing this about the hot water temperature, this starts to tell us we'd like to have a little bit cooler hot water temperature to satisfy our heat. We need to make that decision and do it judiciously. How about that water source heat pump? Well, we think of water source heat pumps as heating or cooling the space. But on the other side, when we're cooling a space or an airstream, we're rejecting water heat into a water loop. So we can take that water source heat pump and use it differently. Now, these aren't designed to use outdoor air, but we can put them in an exhaust airstream. And in the wintertime, we might be exhausting air from a building at 65 degrees. Well, here's an example. We're exhausting the air at 65 degrees. We want to heat the fluid. We can get about 140 MBH of heating out of this heat pump. And we can take that fluid from 95 degrees and heat it almost 20 degrees up to about 114 degrees. So simply by applying this water source heat pump in a little bit different manner, we can also provide heat for our building. Now, what happens to the capacity and the efficiency of this water source heat pump? Again, as the hot water temperature goes up, our capacity goes down, that blue line at the top, and our COP goes down. Now, the capacity isn't affected as much. So that's good news, only about 6%. But the efficiency goes down by 41%. So this is important when you're talking with your clients about electrification of heat in the buildings. So those are some air source products that we can use. How about water-to-water units? On the left is just a chiller. It has a chilled water stream and a condenser water stream. On the second one on the left at the bottom, that's a heat recovery chiller. It has a second condenser bundle, and we don't need any heat exchangers to keep the heating loop clean and without getting debris from the cooling tower. There's a modular unit in the middle, and over on the right is a water-to-water heat pump. These are all simply examples. Now, what we're going to do, we're going to think of things differently, and that is, rather than thinking about the capacity and about the efficiency, what the goal here is to decarbonize, to reduce the carbon emissions. So let's apply these units into systems and find out, how do the emissions change? To do that, we're going to use this graphic. Across the horizontal axis is the heating fluid temperature. What hot water temperature are we sending to our building? And then on the vertical axis, how much do the emissions increase? Because as the efficiency goes down, the power we use goes up and the energy we use goes up. And when we have to buy that electricity from the utility, we will have emissions, unless it's a zero emissions utility. And I don't think there are a whole lot of those available today at this point. So now let's look at these different pieces of equipment and find out, how much do the emissions increase when we go from 95-degree heating to 135-degree heating water temperatures. So we're going to take the first two, the air-to-water heat pump and the water source heat pump. We see that the emissions go up a lot for the water source heat pump. They don't seem to elevate as much for the air-to-water heat pump. However, remember that we ran out of heating capacity. So we're not getting the same heating capacity when we get to 135 degrees. Next, let's look at another piece of equipment. Let's look at that water-to-water heat. the emissions go up significantly for the water-to-water heat pumps. How about those chiller heaters? Again, the emissions increase a lot. And when we look at centrifugal chillers that are making cooler water temperatures, they're increasing also. Now, when we want to decarbonize, we're trying to reduce the emissions. And a lot of times people just say, I'm going to put an electrified heater into the building using one of these pieces of technology, and I'm going to use the same temperatures as I used when we had boilers, 135 degrees. But do we really want the emissions to increase by 60 to 80%? And the definite answer is no. We're trying to decarbonize. And what we need to do, we need to think about these hot water temperatures. And we're seeing a lot of designs today in the range of 105 to 120 degree hot water temperature. Now, we need to change our coils, yes. In the existing application, we might need to retrofit some of those coils. But when we want to reduce emissions, we need to really make sure that we are considering the hot water temperature, and the lower, the better. And that is within your hands. It's your choice, and you can really help the entire climate decarbonize, not just the building. So we've now talked about the different units. Now we're going to look at how we can apply the equipment into systems, how they unload. So let's get to doing that. Again, you can decide the hot water temperature. And you need to think about, when you're looking at the units, what's the intent? Are we trying to provide full heating? Are we trying to recover heat? What's our heat source temperature, whether it's outdoor air or if we have a different source of heat? Next, particularly if it's a centrifugal chiller, but for all units, how well do they unload? Do they keep their efficiency? Are they able to operate at the conditions that we want them to operate at? And centrifugal chillers, if we're recovering heat, generally need to be loaded more fully in order to avoid what's called surge, which is, it can be catastrophic for the chiller operation. So where do we start here? The next, we also need to consider defrost, and we'll talk about that. The more you know about your system loads, the better you can size your units. This is an example of heating and cooling loads for a hospital as modeled by Pacific Northwest National Laboratories. Now that looks nice, but what's even more useful is that if we take these loads and put it into a different graphic from the highest cooling loads to the lowest cooling loads, and then the simultaneous heating loads. Now we can start to make some decisions. In working with our clients, what is the goal? Do we want to do heat recovery? In that case, we want to size the unit when we have a lot of simultaneous heating and cooling loads. So in this case, it'll be a fairly small unit. Are we looking at doing full electrification? In which case, we have to have the unit sized to provide all the heat that we need at any condition. If that's too expensive, are we willing to compromise and make it significant electrification, where we will have some backup heat that could use fossil fuels at the site? And then, particularly again, for centrifugal heat recovery units, we want to make sure that we keep those units loaded. And usually that would be a similar sized unit to a heat recovery unit. So the first thing we want to make sure we do, we want to know the loads. Next, a lot of the heat pumps that we're using today were originally designed for cooling, and we're now applying them to provide heat. They have some limitations. One of those limitations is there will be a minimum flow rate. And since the capacity is proportional to the flow rate times the temperature difference, if we have a minimum flow rate that says we're going to have a maximum heating delta T, usually that's in the range of 15 to 20 degrees. Quite often, existing heating systems or systems in the past have been designed at much higher delta T's. When we apply these pieces of equipment, we will have some limitations. In fact, oftentimes when we select it, we will be very close to the minimum flow rate. So what that tells us is we will have constant flow through that unit when it's doing its heating. And that is going to educate and show us what system configurations make the most sense. And it's probably going back to primary, secondary systems. So here's an example. We have two units in the system. In this case, one is doing cooling, one is doing heating, but either can do heating, either can do cooling. So let's look at how the system is put together. This system is put together, first of all, we have some isolation valves, and they will put the units either into a cooling mode or into a heating mode, depending on what the building needs at this point in time. This also keeps the system simple to operate, and I'll show something in a couple slides that will really give you an example of that. Next in this, we have our heating and cooling plant. And that heating and cooling plant, we will have constant flow through the evaporator of the chiller. We'll have constant flow through the heater, now the condenser of that heater. In the heating mode, we can have the units. We can also have the units in the cooling mode. Now, one of the reasons this can be simple is the heating flow rate might be different than the cooling flow rate. All we have to do to take care of that is to put a variable frequency or a variable speed drive on those pumps and have them at two different speeds, one for the cooling mode flow rate, the other for the heating mode flow rate. It makes it simple. When the unit switches to one mode, the drive on that pump also changes. That allows you to be flexible and use these units for heating and cooling with those different flow rates. Next, we have the decoupler or the bypass line between the supply and the return, both on the heating side and on the cooling side. Then we have our heating distribution loop and our cooling distribution loop. So this makes a very simple, elegant, and flexible system for you to get the cooling and the heating out to the building, and in order to operate different numbers of heaters or chillers at different times of the year. Now let's talk just very quickly about defrost. On an air-to-water heat pump, we are actually taking that outdoor air, say at 30 degrees Fahrenheit, and we're cooling it. And if we're cooling it, we're going to also condense some water on those outdoor coils. Well, when it's below 30 degrees, it's going to become frost or later on ice if we build it up enough. So what the units are designed to do is to melt that frost. And in order to do so, it reverses the operation to do that. Well, a unit doesn't operate both in cooling and heating at the same time or in heating and defrost at the same time. So one way to take care of this is to actually oversize the units so that a part of that unit can provide heating while the other part is defrosting. That costs money for the building owner. Another thing we can do, we can increase the number of circuits, either by having modular units or by having packaged units with multiple circuits. Most of the units will have controls. They'll defrost for a certain period of time, and then they will come back and provide the heating. But if all our units go into defrost, or if we only have one unit that goes into defrost, we'll need to have some backup units. It could be a full additional unit, it could be a boiler or a different fuel. So defrost is important. This is probably about a 30-minute presentation by others who know a lot about it. We did it in about 1 minute. So you're going to want to dig into it more when you get a job where you're looking at that needs defrosting. The next thing we're going to talk about is with respect to heat recovery. And that is, where do we put that heat recovery unit into the system? To do this, we're going to take an example. In this system, we have two 500-ton cooling-only chillers, and we have one 200-ton heat recovery unit, and it can satisfy 3,000 MBH of load. The system's designed at a 16-degree chilled water delta T. Now, our operating point at this point in time, and that's going to change throughout the year, is 550 tons with a heating load of 2,600 MBH. The heat available is our cooling load, 550 tons, plus the electricity we're putting into that compressor, called the heat of compression. So if we use a coefficient of performance of 4, we have over 8,000 MBH of heat available. So we can recover all the heat we need for this heating. We need to load that heat recovery unit to about 175 tons in order to satisfy that heating load. So let's look at how the system could be piped and whether or not that provides the heating that we want at this point in time. Most of the time when I see hydronic systems with heat recovery units, they're piped in parallel on the cooling side with the cooling only units. So this is at design conditions. We have a 16-degree delta T. All the units provide cooling during the summer, and they're all fully loaded. The issue is, at this point in time, recall, we have about 550 tons of coolant. We need 2,600 MBH. In this primary secondary system, we're going to be mixing bypass chilled water with return water from our system. So the return water temperature to the cooling units is 52.6 degrees. And the capacity of the units is proportional to its flow rate, constant in this case, times the temperature difference, 52.6 to 40 degrees. When we look at that heat recovery unit, that's 157 tons. It can provide 2,360 MBH of heat. That's not as much as we want, so we have to purchase some more heat. There's enough heat. We could recover all the heat for this heating load, but because of the way we pipe that unit into the system, we cannot. So this is not optimal. What's another option? We could put that heat recovery unit on the load side of the bypass line. When we do that, it will now be fully loaded because it gets the full return water temperature of 56 degrees. So in this case, this unit is going to be loaded preferentially. So we have our heating load. We're going to produce 3,000 MBH of heating. We can fully satisfy the heating load. We have to reject a little bit of heat from that heat recovery chiller, but we can satisfy the full heating load. A great idea. This is called preferential loading. Now, an elegant way to put the system together. We can put the system together by putting that heat recovery unit in a side stream position. That is, it has its own pump. It pulls water out of the return water stream. It cools it, but it cools it just enough to satisfy the heating load. So now this unit is a heater. We control it to maintain the hot water temperature that we want. So the other chiller will take care of the rest of the cooling. So in this case, the heat recovery chiller loads to 174 tons. The cooling chiller takes care of the 376 tons. The rest of the cooling load, we exactly satisfy the heating load, and it is simple. It's elegant because we pipe the system, we design the system properly. When you're doing heat recovery water-to-water units, really consider putting them in this side stream position. We don't have to purchase any heat. We don't have to reject any heat from that heat recovery unit. It is simple, reliable, and as our presidential member, Kent Peterson, said in his address in 2007, elegant design. Now, let's move on to our next examples. We're going to take two different building types, and we're going to put them in different climates. And we're going to use the ASHRAE 90.1 modeling done by Pacific Northwest National Labs. So we're going to take a hospital and we're going to put it in the climate zone 3A at Atlanta, Georgia, where ASHRAE headquarters is an example of a climate zone in climate zone 3A. The hospital has 540 tons cooling load, needs 3,000 MPH. The 20-year extreme temperature in Atlanta is 6 degrees Fahrenheit. So every 20 years it will get that cold. The 50-year extreme is a bit lower. Hospitals are required by ASHRAE standard 90.1 to heat domestic hot water, and that's going to be about a 40-ton heat recovery unit. The requirements, because it's a critical load, a critical building, is N+1 heating redundancy. So we have an additional heater, and we'll also have an additional chiller during the daytime. We looked at that. This is that hospital profile we looked at earlier. And we might have full electrification, significant electrification, or heat recovery. So let's look at those three possibilities for this particular building type. To fully electrify the system, we can select 4 units, each at 996 MVH. Now with N+1, we're only actually going to use 3 units at a time. So that's a little bit less than the 3,000 MVH that we need. If it's close enough, we can select these units. Otherwise, we'll have to select the next size air-to-water heat pumps. These are each 200 tons. So we satisfy both the 550-ton cooling load and the 3,000 MVH heating load. And we have 1 unit for redundancy in either heating or cooling. And this is a simple system. One of the issues with this design might be that these air-to-water heat pumps are too expensive, and it goes over the budget. So that might take us from full electrification to significant or partial electrification. We might also want to look at modular units, because then we don't have to buy another full unit size. We can just buy a modular size. And this is a significant advantage of modular air-to-water heat pumps. In this case, we have 10 modules. And the 10 modules gives us 296 tons, that's N+1, and 2,280 MVH. But for our N, to have our redundancy, that's about 266 tons of cooling and 2,000 MVH of heating. So that means we have to have some type of backup. In this case, we might have boilers that are less expensive, but they only have to be 1,000 MVH. They could be fossil fuel fired or heating. We're going to have to use more electricity for the heating if we use electric boilers. However, it'll be less expensive. Then we still have, from the cooling side, have 2 275-ton cooling-only chillers. So this will provide full cooling redundancy, full heating redundancy, have a lower installed cost, but we may not be able to fully electrify the system. This system will look like this shown on the screen. We have the 2 cooling-only chillers at the bottom. We have the modular air-to-water heat pump, which can either provide cooling or heating, depending on what we need. And we have our boiler for makeup heat, our backup heat. Our third system example is going to be full electrification, but recovering heat from our system. So we looked at that load profile and decided this should only be about 120-ton unit that can provide 1,860 MVH of heat. And at the minimum load, cooling load, it can still provide 600 MVH. Now we have a smaller modular unit with 7 modules, and we have 2 of them, so we have full backup heat. We have 1 cooling-only chiller, about 215 tons. Here's the summary. We can fully electrify either with heat recovery, the last alternative. We can fully electrify with full electrification with just 4 units. Now with this heat recovery layout, here's what our system might look like. We have the one cooling only chiller at the bottom, 2 air to water heat pumps, and that dedicated heat recovery unit that is put in a side stream configuration, both on the chilled water side and on the hot water side. That makes operation simple. So we had 3 different examples we could use on this hospital in climate zone 3A. We can use full electrification, 4 packaged units. It's simple, but it might be over budget. Significant electrification, an air to water heat pump that's modular, 2 cooling only chillers, and some boilers. And finally, full electrification, which uses heat recovery, which will probably be more efficient. Again, that will likely be a lower cost than the first fully electrified system. Now let's move on to something a little bit harder. We're going to move to a secondary school in climate zone 5A, outside of Chicago. We see our tonnage at 263, 2,448 MBH of heating. The issue is the outside air temperatures, -2 degrees for the heating design. The 20-year extreme is a cool -21 degrees Fahrenheit. The 50-year -26 degrees Fahrenheit. Now I live a little bit further north than Chicago. This is our thermostat from a few years ago when we had the polar vortex, -34 degrees. So we're going to select 115 degree hot water temperature. We want N+1 heating because we always have to supply the heating. But if we lose a unit during the summertime, we want 67% of our cooling. But we don't need a full cooling, and we're going to have a changeover system. Now, these cold climate present some challenges, but we're not going to use my words. We're going to use the words of the ASHRAE position document on building decarbonization, which was published in June of 2022. The first one is in very cold climates. We need more research in heat pump technologies so we can operate at those lower temperatures. In these cases, we might need fossil fuel boilers for now. I heard just earlier this week that there is a municipality near Chicago who is no longer allowing natural gas lines to be put in. Today, that's going to be hard in order to heat the system using outdoor air. So we'll likely have to find some other source of heat. And I'll talk shortly about that in a couple slides. We need to make sure that the electricity is available from our utility. We need to look at the flexibility in our system design and perhaps storage capabilities. We'll look at that. And we need to make sure that we're reducing the loads by making the buildings more efficient and reducing those loads through better windows, lower infiltration, and things like that. So the first part is, let's take 3 of those air-to-water heat pumps. At 25 degrees, they can satisfy 4,800 MBH. They were oversized for heating. However, when we get down to that -21 degrees, they aren't going to be able to provide any heat. And we're going to, in this case, use boilers for backup heating. Whether they're fossil fuel or electric is your choice. But if they're electric, you have to have that electricity available to the building. So the system would be set up like this. And this is in heating operation below the 25-degree ambient. Now, how often are those boilers actually going to run? Well, that's going to depend on the winter, but these are average temperatures. So the average low temperature in January in Chicago is 22 degrees. So we can get most of the heating and not have to use a lot of that backup, although we need to have it in place. So when we think about that backup heat, we need to look at how much is it actually going to be used and how does that affect our goal to decarbonize. Our second system we're going to use some modular air-to-water heat pumps which can get down to 0 degrees Fahrenheit. And we're going to provide 10 modules with N+1 capabilities. But then below 0 Fahrenheit, we're still going to have those boilers available. They'll run even less than the first one where we were using the packaged air-to-water heat pumps. So the system would look like this. Pretty simple. Able to heat the building down to 0 degrees Fahrenheit. Again, if the boilers use fossil fuel, we may not get to full decarbonization at the building site. And we're going to need to work with the building owner, with the project team to find out on a particular application what is going to be best for that school. Another thing we might be able to use, if we have a geothermal field, for example, we have a bore field to which we reject heat in the summer, we extract heat in the winter. We can put a unit that's taking that heat from the bore field and putting into our heating system. This can significantly reduce or eliminate the necessity for backup heat. However, bore fields can be expensive. So people are looking for all kinds of different ways to provide the heat. Another way we can do it is using a thermal energy storage. For example, ice or water storage. But it's used a little bit differently. And the goal here is actually to store heat. And we store heat in an ice tank by melting the ice. So in the daytime, when normally we would be on air side economizers and sending all our heat outside, instead, we could be melting the ice, store it during the daytime, and then freezing those tanks in the morning when we need heat. And these are systems that people are considering today, and they've already been installed in a number of applications. Let's talk just very briefly about financial impact. Oftentimes, these systems might be higher cost. From a building owner standpoint, they'd love it to be the same cost. That's sometimes hard to get. So let's look for incentives. Are there any local utility incentives? Are there ways that we can get those money in rebates or financial incentives? We also need to look at what's the climate from a fee standpoint. New York City Local Law 97 has some significant fees for CO2 emissions at the buildings. Canada has carbon taxes. So those need to be put into our thinking and put into our analyses. Some building owners also affix a carbon price. And that is, they have a corporate goal to reduce environmental emissions and decarbonize. So internally, they have said, this is the value we place on CO2 emissions. These can all be and should all be looked at as we're considering the financial impact of a project. So let's summarize with some general guidance. The first thing we need to do with our clients, our customers, is to define the intent. What's their goal? How much are they willing to spend in order to get to that goal? Understand the limits of the equipment. What's the heat source? Is it outside air? Are we recovering heat from sewage? That's been done in a number of ASHRAE award-winning projects throughout the country and throughout North America. What's our hot fluid temperature? Remember, selecting 105 to 120 degrees opens up a lot of efficiency and a lot of different options. And then, as we're applying this, we could make the system very complex, hard to understand, and hard to operate. Or we could make it a primary, secondary system that people have used since the 1970s, with the pumps operating at 2 speeds, one for cooling, one for heating. We put the heat recovery units in those side stream positions. We develop the sequence of operations so that the building operator knows how it's intended to operate. And we make sure that we have the operators on the team early in the process in order to make sure that when we turn the building over to them, they can actually run it and get that decarbonization, the reduction in carbon emissions that we're looking for. I highly encourage you to look at the ASHRAE position document on building decarbonization that's available on the ASHRAE.org website. It's been a pleasure and an honor to be with you to talk about decarbonization and electrification, and we look forward as ASHRAE to supporting you fully as you embark in decarbonizing and electrifying buildings.